Okay, now that we're done talking about just what the Bode plot is and even how to sketch one by hand, now we'll talk about interpreting the Bode plot in a certain way. And it's going to be kind of analogous to root locus. What we're doing is using information about the forward path transfer function to determine performance and performance measures of the whole closed loop system. So we're going to be given, say, the Bode plot of this forward path gain, this G of S. And from there, determine some closed loop performance measures. A couple of restrictions for my course, just to keep it semi-simple. First, we're talking unity feedback, or unity feedback. Gain in this feedback path is 1. The other thing, this G, if you have a Bode plot of it, it has to be stable, meaning all poles in the left half plane. We're going to require also that all zeros are in the left half plane. That type of system is called minimum phase transfer function. So given that, what can we learn from the Bode plot? And remember, a Bode plot could be determined experimentally. Someone could take this G of S, give it a bunch of inputs of sine wave inputs at different frequencies, measure the phase and amplitude of the output, and experimentally get a Bode plot. So you could be getting a Bode plot without knowing the transfer function. You're going to kind of interpret what the system is or how it works from the Bode plot itself. And what can we learn? Here's the bullet points of what we'll be able to learn. First, what's the system type? Remember, that's when we talked about in time domain analysis, steady state errors and system type. So we can learn system type and the error constant. Those two things, steady state error, that's time domain's performance spec. We can determine relative stability. I'll talk about that later in terms of gain margin and phase margin. We'll talk about those later. Then absolute stability. Relative stability is kind of like how close to being unstable is it? It's more of a quantitative measure, not just simply a yes or no, it's stable or it's not stable. The peak overshoot, which was another time domain spec, and also the resonant peak, which is sort of a peak overshoot in the frequency domain. We'll talk about that later. The bandwidth of the system, which is a frequency domain spec. And all of the above, we can do it for alternate gains. That is, if we put some constant gain in front of this G here, we can determine what it would do to all those performance specs, all using the Bode plot. Let's get into the first couple things, system type and steady state error. If you were given the transfer function, you found the system type by what's the power of any S's in the denominator, poles at the origin. If it's single S to the 1 power, that was a type 1 system. If there was no such S, that was a type 0 system. And if it was an S squared here, a double pole at the origin, would be a type 2. And then we found the error constants by ignoring any poles at the origin and setting the other S's to 0. In this case, it's a type 1, so our error constant is going to be k sub v, or the error to a ramp, kind of a velocity error. And what is the k sub v? It's going to be 20 times 4 divided by 2 times 5, or 10, or 20 divided by 80 divided by 10, which is 8. This is not a log scale 8. This is just the actual error constant. But from the Bode, if you know one or two things, remember this, the power of any poles at the origin told you what the initial phase would be and what the initial gain slope would be. So now if we're given the Bode plot, we can kind of go backwards. So if you, and the initial slope is going to be a multiple of 20 dB per decade. The initial phase is going to be a multiple of 90 degrees. So by looking at those things, we can know the system type. We'll know the power of S in this denominator. And then the KV, the K naught on the Bode plot, remember when we did that? It was calculated the same way you calculate the error constant. So if we look at the graph and determine what that K naught is, we can determine what the error constant is. We'll do a couple of quick examples. So the blue line is what you're given. That's the Bode plot. You want to look at this initial asymptote. It's this dashed line, so we would maybe draw that or use a ruler or something to determine that. If you looked at that and calculated the slope, it's minus 20 dB per decade. Easier is just look at this initial phase. It's minus 90. That right there tells you it's a type 1 system. And now for the error constant. We're looking at the omega equals 1 frequency line. It's the 10 to the 0 line. It's this line up here. And we're looking for where this asymptote, this initial asymptote, crosses that omega equals 1 line. And that is right here. We're looking where the asymptote crosses. This is where the gain crosses. We don't want that. We want where the asymptote crosses. And go over here and see where that is, dB. Kind of hard to tell exactly where it is because the increments are so large. But it's going to be, I don't know, 10-ish dB maybe. Actually 4 dB. Then you'd have to undo the dB, divide by 20 and raise to the log 10 power. Undo the log. So the real KV would be 1.6. Again, you couldn't quite do it that accurately by eyeball. You can't tell if that's 4 dB. That's the idea. Here's another case. Initial slope's obviously 0. It comes in at 0 phase, so it's a type 0 system. Here's the omega equals 1 line. It crosses, asymptote crosses it right about here, over here, which is, I don't know, maybe minus 10 dB. Hard to do by eyeball. It's actually minus 12 dB, which is 0.25. Undo the logness of the dBness of it. So there's our error constant, and it'd be hard to do it by eyeball. And it is K sub P because it's a type 0 system. So anyway, with the error constant and the type of the system, you know the steady state error. We'll get into the other stuff in subsequent videos. So, interpreting the Bode plot.